Sure, we'll record it, yeah.
Yeah, sure.
Here we go, and we are dynamics. We are exam 3 review. All right, only 4 minutes. It only took us 4 minutes. I got a sign-in sheet if you want to be all official in that. And great. All right. So, welcome to exam 3 review. As I usually like to do, here's the main topics that we've covered since exam 2. Angular kinematics, rigid body motion, RBM is rigid body motion. Did velocity analysis, and we did it. You could say that we did it in 4 different ways. We did vector math. We did 3 diagram method. We could use vector triangles. And we did ICR, instantaneous interruption. And then we also had an acceleration analysis. And that was could be done with vector math or the 3 diagram method. Really, we didn't really do the triangles, and there is no ICR thing to really do. If we were looking at the equation sheet, which I didn't bring one with me, this is I think it might have been updated in some ways since then, but these are like the basic equations that we're dealing with for this exam. So, without further ado, does anybody have requests? We're taking requests. We have these old problems from the U.S. Coast Guard Academy from years back. Some of them I wrote the solutions to. Some of them I didn't. And actually, some of these right here, there weren't enough practice problems. So my good friend Sean Munnis picked out some of these other ones. So these aren't old exam problems. They're just problems that he said, hey, here's ones that you ought to try and practice on. So, and then also I have uploaded, at least for my class, a bunch of problems from Bedford and Fowler, and then also some that I picked out of Beer Johnston. So I think this might happen to be the same one as one of the other ones in there. So does anybody have any? Okay, Monica.
Can you start off with a velocity analysis S22?
This guy?
Yeah.
Okay, cool. All right, so this crank AB is rotating with a constant angular velocity of 5 radians per second, and the direction shown to be clockwise. Determine at this instant the angular velocity of BC and velocity of piston C. So what way do we want to do this one? We want to do it in multiple ways? Or so what do we want to do first? Anybody got a request? We'll do the diagram first. Sounds good.
Can you confirm it with a vector triangle as well?
Sure, absolutely. Although sometimes I have to that really makes me think. Let's try, but that's good news. It's good news to make you think there. But so I'm not guaranteeing anything there. Therefore, I'm not. Therefore, that's my CYI to CYA. Sorry, that's the right acronym to say. I don't know for sure that I'll get it right. So anyway, we'll start off with in a 3 diagram method. Let's get this velocity first. We get this one. The velocity of B. Get that angular velocity of 5 radians per second. So V is just going to be 5 times 0.3. And I think I could do that in my head, but I just went ahead and peeked because that's showing a distinct lack of confidence. Okay, so now for the 3 diagram, what we want to do is we're going to take a look at this member right here. And we start off, we have a velocity coming that direction, VB. This one is going to have, he says, is 40 degrees, so that's right there. We're going to place the known velocity at both locations here. Kind of shorten that up because it's supposed to be a plus and didn't leave enough room, but that's okay. It's a little crowded up here. Okay, and have that relative velocity like this right here. So what do we know? We're going to try to find the acceleration of c. So we're writing it for this location right here onto the thing. And it's going to be the acceleration of b plus the acceleration of c with respect to b. You're right. Going on autopilot. Whee! I'll start thinking. I got to remember to think. Thinking is harder than not. Okay. So here, let's just make an assumption that that goes clockwise, counterclockwise. Omega BC. So that's going to make this thing go up. So this is going to be our VBC. Sorry, C with respect to B. And we know that VB with respect to C as a magnitude is going to be that omega BC times the length of BC. So we break this down into, I don't see, you know what I think in the X direction is going to be our best bet, maybe? Yeah. Actually, I think we're going to have to do the Y direction. No, I think X direction is going to be better. Let's just try it. Sometimes we can like see which way it's going to be to start with. So I'll just assume the positive again right there. Right, we'll just write it as if it's positive. So that's going to be that 40 degrees right there, right? So we'll say that VC times the cosine of 40 degrees, it's positive as we drew it, it's going to be equal to VB, which is 1.5, and nothing, right? So we can find VC. That's just going to be 1.5 divided by the cosine of 40 degrees. So that ends up, if I can find where that went to, 1.958. And then, so therefore, in the Y direction, we could say that now we know, and by the way, it was positive right there, so we have this correct. We could actually, if we want to, commit to, there's our VC coming up that way. Sure.
Just so I know, like this is, so if say it was negative, it's easier to just stick with that negative, so you plug it in to say that other direction instead of just redoing the diagram.
Yeah, I would even, yeah, exactly. I'd even, sometimes I might, I'm not 100% sure I've always done this, but I probably would tend towards putting that, writing the thing out and specifically putting the negative inside the parentheses. So I would write out the equation for what I see on the diagram, and at the very last second say, oh yes, but the quantity is negative. So that, I mean, that's like just maybe it's a silly little thing, but maybe to try to keep, make sure I didn't, draw a blank and totally forget about it to fix that. Yes.
Can you just explain real quick on the last diagram, like the rotational motion one?
Mm-hmm.
Why is BC with respect to B just drawn upwards? Just because that's like the velocity due to the rotation?
Yes, yes, yes. In the third diagram, we pretend it's in pure rotation. And in that pure rotation, it has to be perpendicular to the link. And I didn't know that necessarily that it was going to go up, but I did confirm that sense, we knew it had to be, that BC had to be on that line of action. So with the X direction, we said, yep, it has to be up because this is the only thing over here. It's got to be horizontal. So if it has to move that way, then it has to be going upwards. So here we can go ahead. I could write out the equation here, but I could just stick the 1.958 right in there. And now it's going to be the sine of 40. It's going to be equal. Okay, so there's nothing right here, so I'll put a 0 in there just as a placeholder. Plus my omega BC times the length, which is 0.5. And we can find that omega BC is going to be equal to the 1.958 sine of 40 divided by 0.5. And it should be equal, if I did this right, to 2.52. I would like to have an extra decimal place. Thank you very much. 2.517 radians per second. And if there was any twist on, I would call a twist maybe, but maybe like my perception, maybe not a student's perception. But I say the twist was we asked for the angular velocity first and then asked for the actual velocity. So it's kind of a, might lead you towards thinking that you had to get the angular velocity first. I just point those kinds of things out. It was, I don't know. I don't know if any that would be a trap for anyone in any way, but it's a little bit of a thing, maybe. Now, what's a really good idea is to, well, let's do the vector triangle first, right? Because you asked for it. So remember that this is the equation that the triangle describes. And so we know VB is horizontal. And we know that we're going to add in, and we can see from here that this is, we're going to add the next thing. So the next thing needs to come off of the tip of VB. I'll label VB. So let's say that we didn't know this above. Like we're trying to approach it fresh without having seen this other thing. We can see from here that the relative one, and that same thing that Michaela asked about before, like what direction does the relative one, well, it has to be perpendicular to the link. So along that mindset, we know that it has to be along that length right there. And really at this point, we don't know whether it's above or beyond, but we know now also the sense of C, right? So we have this, if we wanted to, we want to be really careful. We could actually measure and make that to scale if we wanted to try to get things out. But we know that, so we know that it's going to be from on the tail of this because it's at the equal onto the thing. So we get that conclusion that it has to be like that right there. Well, try to think of the other way, right? Because we know that it has to be the sense, and it's got to be attached to the tail of this vector. So there's like, it can't go down below, right? Why is it attached to the tail? Well, I think of it as being when we're adding, we go nose to tail for the things we add, but then the thing that equals goes tail, tail, nose, nose. So we were going to add to the nose with whatever this is. And so we're then so this thing has to be associated with the tail. That's there's other mnemonic things that you could use as part of this, but from that logic, this has to be coming upwards like that, and then this one has to come up that way right there, and has to be 40 degrees, and this is an easier one. So now, if you wanted to get, let me see, I got to write this right. I was about to write. There we go. So from the triangles, we would say, well, we know that this is 90 degrees and that's 40 degrees. We could figure out this other one right here, but we could, either way that you want to go, we could say the VC is going to be VB divided by, this should be the cosine, right? To get the hypotenuse. Because that VC is the hypotenuse of this, so we would want to, this is the adjacent, so we would want to divide VB by the cosine, which is adjacent over hypotenuse. That would give us the hypotenuse. And the same thing true over here, but now I always got to be careful with this. Is it going to be multiplied or is it going to be divided? We want the rise, so we need to multiply, right? So we need VB times the tangent of 40 degrees.
So on one of these problems on the exam, would you be asking us to solve a given triangle or just to confirm our answer?
I probably just to confirm your answer would be the typical thing that I would say, if I even asked it. It's not a point of emphasis most of the time for me. I'm just kind of a nice thing to keeps your skill up when looking at it. It's a really good idea to just to have that extra sanity check onto things. So we know that we would get the same values right here. We should get the same values as we got up above. Of course, we didn't get the relative motion one right up in here. So I guess instead of being lazy, I'll get out my old Hewlett-Packard calculator and take and say, here's a 1.958 divided by the cosine of 40. Well, this is identical to the thing up there. No, is it? No, it's not. Okay. So see 1.958 and 40 cosine. You better be equal to it, right? Didn't come out right. Did I do something wrong? Oh, that's what I did wrong. Yeah. You were about to tell me I did it wrong, right? There's 1.5. This is 1.5. Yeah. Oh, that makes sense. Yeah. B was equal to 1.5. Duh. Yeah. So we end up with it's identical thing to the right there. So it's got to be the same. And this would be 1.5 times the tangent of 40. So 1.259 meters per second. And that we know that omega BC is the velocity of C with respect to B divided by the length of BC. So 1.259 divided by 0.5. And you get the 2.517 radians per second. And then lastly, I'm going to do an ICR. I see people are still writing down, so I didn't want to shift this right away. I believe so. I'll double check. It's a good thing to double check. You are, they got the little thing right there, recording in progress. Yeah. I think that he just said yes. No problem. It's good to help me out that way. I need that help. I hate hybrid things. And I don't resent the having to do it. I didn't mean to sound that way. Go ahead, please. Sorry, this would be, I forgot my parentheses.
Oh, 0.5.
Yeah, I'm sorry. Yeah, it looks a lot like cosine, doesn't it? Yeah, I just, for whatever reason, went a little manic and left off that last. When doing the ICR, it's always good to try to remember. We've got to be very, very careful not to draw the lines for the ICR thing in line with the velocity. They have to be perpendicular to the velocity. And one thing that can help you remember that is a lot of times you're extending the line of a link, right? So this link right here, you could just extend the line of the link. You know that's going to be one of your lines because the velocity right here ends up being in line with that. Now you remember the velocity has to be in line with here, so you need to draw something that's in perpendicular to there. So right here becomes the ICR. For some people, ICR seems pretty simple, but there's other people that have a real hard time with it. So don't feel bad if you have if you see somebody else and they're like, oh, the ICR is right there. For whatever reason, just some people, it just takes practice. So don't feel dejected. With a little bit more practice and just a little bit of concentration, like just remembering why you made a mistake when you made a mistake, so that you can kind of organize how you're approaching the thing, whatever it takes for you individually to make that so that you can find the ICR. But then once you're getting good at it, it's a pretty easy method, except for when the link is at a weird angle and the ICR is up into the heavens and you have all these weird angles. Trying to find them can be kind of a pain, but this is a nice one because we have a 90-degree thing going on there. So all we're left with is just double checking our angles on things, right? So we knew we had this, and we knew we had an angle that was like that right there, which was 40 degrees. I'm just reminding ourselves. So we had something that was perpendicular to it right there for our ICR. And now we got to try to figure out our angles. One way that I might try to do it is I would say that this was 40 degrees right there, right? Using sort of like the parallel line thing. Well, this is going to be 40 right here.
Yeah, but then the angle between that would be 50 because it has to equal 90.
Exactly. There's a bunch of different ways that you could try to use your geometry, but what's really hazardous is if you draw it at 45, and now you're kind of lost. So you might even want to lean towards making a side sketch where you exaggerate, the thing, just to double check if you have some kind of uncertainty going on there. But this is pretty close to right here. So that's how I would have approached this thing. And so let's see, I got to remember that this is B and this is C. So we already knew that this direction, that was VB. So that means we have to have our omega. And when we gave the answer, by the way, of all those omegas, we should have given our direction with it. Should be understood that it's asked for. If it didn't explicitly get asked for, it's sort of like, unless we ask for the speed, then it's pretty certain. So this is going to be RB with respect to ICR. And this is going to be RC with respect to ICR.
So our omega goes counterclockwise because velocity is going to the right?
Yes, yeah, because you take a look at the known one and you say, well, that's going this way, and the only way that could happen is if this is if omega BC is counterclockwise. And then because of that, we do know that this has to be upwards. So we get the RB with respect to ICR. Easiest way to do that, this is now the run, and this is the rise. So we're going to, once again, we would multiply this length that we know right here, this LBC. Am I saying that the right way? I think so. We want to, I'm looking for it. Ooh, wait.
Would you do law of sines?
I would only do law of sines if there's no right triangle involved. But you could always do that, yeah. But with the right triangles, there's just a little simpler. You could just take the tangent now, because the tangent is rise over run, and we're multiplying by the run so we can get the rise. That's my thought process there.
It makes you feel like, yes, you got it.
Okay. Well, hey, it works. So there's nothing wrong with it. So 0.5 and the tangent of 50. And if we were to do that, I don't think I have the in-between number for whatever reason, because my good friend Dr. Alicia Garcia wrote the solution. I miss Alicia. I miss Alicia's son. He was cool. Skyven. Skyven would come into my office all the time. Hey, Ted. He was probably about 4 years old. I was his hero. And then like he would play. I had like all these toys in my office. He'd always play, and then I also had a collection of just junk and things. One day I look over and he's got this razor blade that I had. He's holding it up like, ah! I had made my office childproof. Apparently, I had to go confess to Alicia that I'm so sorry, but just I have to admit I was not a good. Yeah. And then when I was leaving, I gave him like a bunch of toys, and she made him to give back a couple of them. Oh, he could totally have them, I swear. Anyway, Skyman was my buddy. He probably doesn't even remember me now. It's been 5 years. So anyway, take VB and divide by that, right? So we have VB. So we want to find what that omega is. So we divide by this motion. Skyman doesn't remember me. That's just a sad thing to think. Oh, I don't want to think about that. 1.5 was what this was equal to. And 0.959. 5959. So it better be equal 1.5. 2.517. Yay, it's the same thing because it says it right there. And then we also need to get the RC with respect to ICR. I always go back to the one that I know, but you could have done the other way right here. So now we want to take the length of BC, and I'm going to divide it by the cosine of 50, so I can get the hypotenuse. So 0.5 cosine 50, 0.5, 50 cosine divided. 0.7779. You thought it was going to be another 7. Get out of my way. Oh, now I got that stupid thing. I don't know what the hell that is for. And now, so if we want to get the velocity of C, we take omega BC, multiply it by that C with respect to ICR. 2.517, 0.7779, multiply 1.958. Did I get that right? Yeah. Okay. Meters per second. And now we can do a vector. Want to do vector?
I don't even.
There's another problem with the aspect now.
We can do whatever you like. Which one? You okay with the vector math on this one? We can move on to another one. Okay.
Can we do acceleration analysis? It's on page 6.
Okay, let's see which one.
Dr. Deal,
Yes.
can you number these forms?
I really should, I guess. Yeah, can you tell me the year and the title? Because I gave titles to him. Yeah. So which one were you asking? But page 6, what is the title?
It's the one right before the slide. It's the spring 16.
Okay, thank you. I too do not have them numbered. I should number them, but I haven't. Okay. Oh, there is page numbering at the bottom.
Yeah.
Ooh, what?
Saying,
Did I do something in graphic communication to get somebody there?
no, my printer didn't work for when I print out these assignments. And so I have to really explain why.
Oh, I think I understand. Yeah. Okay, yeah, so let's see. Sure. So we have to, let's see, they might have already told us, yeah, they already told us the velocity so that we didn't have to do it. Sometimes that would be like something to, like if when modus operandi when writing exam problems and preparing is to take it ourselves and time ourselves and then see, ooh, this one's too long. So then we look for ways to shorten them. So it won't always be true, but it might be that I would give you what the velocity analysis was right here. So they already told us, well, let me just read it from the beginning. For the slider crank shown, this is equal to 6 inches, and this is equal to 15 inches. And it's rotating at a constant 20 radians per second. So that was constant, that's an important thing, right? When this thing is 70 degrees, and this ends up being 22.08 degrees, save you a little bit of time. Velocity analysis gives you that omega AB is 2.95 radians per second counterclockwise, although that doesn't matter. At the same instant, find the angular acceleration of AB and find the acceleration of A. So the first thing to do for many of these is going to be after the velocity analysis is to find the acceleration from the input link, right? So the input link here is OB. So we'll draw OB. And they gave us, it was a constant angular velocity. Therefore, it has no it has no tangential component for acceleration. It only has a normal component of acceleration that's pointing towards the center. So you could say that the entirety of the acceleration of B could also be written as the acceleration of B with respect to O in the normal direction, which is going to be omega O squared times L OB, lob.
Why is that the case? Why is it not tangential?
Because it's a constant angular velocity. If there had been an angular velocity on the input, then it would have had a tangential. Something good to do here is to recognize the angles, like right away, even before I'm getting the magnitude. We know that's 70, so this right, the 2 has to be 70 right there. And I didn't leave myself a lot of great room here, but this is, what, 20? And this length, we're going to keep it in inches, that's fine. There's no reason to turn it into feet. And we will find that that's 2,400 inches per second squared. Now, go through my 3 diagrams here, try to keep my angles as best as I can here.
I thought that the angular acceleration of AB is 2.95. How did you get 20?
That's OB.
Oh.
Yep. Let's see where I start. Okay, so we know that A is going to be along this line of action. We know this guy is, we got to try to be careful not to make it look like it's perpendicular to it, right? So there's, It's damn close to being perpendicular though, if you think about it, because if you had 70 and 22.09, that's 92.09. So this is really close to being 90 degrees, right? It's not that far off, but we're going to make sure that we're putting in those angles in there will help us remember that, right? That this is AB. My equal sign kind of in the way. So because we know AB, that's a good candidate to be for the one to be that we place as our reference. We can think of it as a reference, but also it's the one that it's going to it represents to us. And I'm just trying to talk and write at the same time. Should be a job prerequisite. That's the one it represents translation, right? This diagram represents pure translation. And I'll make sure this is where it's important to put the 70 degrees right in there. And because we use this as the reference, we pin it. And that plus is also not conducive. Should have written smaller, maybe. We're going to have, we don't know the direction of the tangential, but we can find this right here. Yeah. But with that angular velocity is going to allow us to get the magnitude of this normal, right? That's going to be the A with respect to B normal right here. And because we don't know, and which we, by the way, is going to be AB squared LAB. Right, so we can find that value. We also know this angle right there is the same as that angle. So bear in mind that's 22.08 degrees. It said 0.8, yeah. So here we have to kind of make a decision, and I'm going to go ahead and say that counterclockwise is my guess. So that's going to make this on my diagram be my acceleration of A with respect to B tangentially. Thank you. Well, I thought he was closing the door. So that was awkward. Another awkward interaction. I'm pretty good at them. Okay, so here is this angle right there. We could also tell that that 2 is going to be 22.08. And if you're ever unclear, one way of doing that is to like go and, so I'm looking at this top one and I'm closing it down. Like, oop, this one closed down, so that these have to be the same angle. That's my little mnemonic for myself to try it with when I have a little ruler. By the way, don't be jealous about the new ruler, right? I gave you a ruler, but then I discovered after giving you the new ruler, I found one that has a protractor. But the bad side of it, it's brittle as frickin' as hell. It is really, really, I mean, see, that's why I have tape on mine, because it just immediately cracked. But what a great little thing here. It came with the, you know, it's worse than that. Did you break? Did you break yours?
No, I didn't break it.
Okay.
I got really upset when I thought I lost it.
That's it.
She stole mine once.
Ooh, no, you know, hey, I don't want to have to intervene. Do you know what my parenting, my ultimate parenting technique is? Right, I was a stay-at-home dad, right, when the kids were little babies, right? So I was like, but when they got to a certain age, like, be nice. That was my parenting, right there. But you think about that. That really encapsulates everything. Be nice. Just be nice. Just be nice. Also, if you're watch the movie Roadhouse, that was how he trained the other bouncers in the movie Roadhouse. Just be nice. Yeah. Okay. So that's how parenting is done. So we learned that. But let's go back to acceleration. And so we're writing this thing for the acceleration of A is equal to the acceleration of B plus the acceleration of A with respect to B tangentially plus, I'm going to say normally, but that sounds awkward. More awkwardness. All right. And from experience, we could say that, hey, the y direction is the thing that's going to let us find the unknown, because in this case, the acceleration has to be in the x direction. So we get to put a big old 0 here at the front when doing this one. And this is going to be negative direction.
Have we decided which direction our acceleration at A is going?
Well, no, we haven't. We haven't committed to it yet.
Okay.
Yeah,
We'll do that.
we're procrastinating. Yeah, yeah.
What would happen if we had an
Ooh, what if? I love what ifs.
What if we had a tangential component to AB?
If we knew it already?
No, because we assumed that AB, because we just had a normal component to
Okay.
AB, so we just like say.
You're saying AB, but it's actually OB.
No, the acceleration of B.
Oh, acceleration of B. Okay.
Yes.
Yeah. You were saying AB, so
Yeah.
maybe you meant acceleration of B.
Yes, yes.
Okay, yeah, A subscript B. Okay, cool.
Yes. What would we do if it was a tangential? If we had a tangential component?
It would just make it a little bit more complicated, make it kind of harder.
Okay.
One of our choices might be a coordinate transformation, just because we would have, honestly, it's tough. It's tough to do. So that's one reason why you would write a problem without it in there. You probably would only include it if they were already aligned with the X and the Y because of the nature of the problem.
Right.
You know what I mean? It's tough it's a time sink that I'm trying not to make time the
Right.
thing that you're being tested on.
So that might not be a worry that we have.
I don't think so.
Unless
Unless I just get this mean streak that just say, like I just like, you know what? F these guys. I'll show you. Like I swear I've had professors who did that though. All right. So it's not out of the realm of possibility that I could have a personality change by the time I get from here over to, like, I don't know, somebody could cut me off in traffic and you don't want me somebody could be in the left lane going 55 parallel to another person going 55. And you just don't know what's going to happen after that. But yeah. Nobody wants that. All right, so this is 70. So we're writing it for this part right there. We can see it's negative in the y direction and sine of 70 degrees. Now we go to the tangential one. We see as we've drawn it with our guess, right? It's going to be negative, and it's going to be alpha AB times the length AB, which we recall was 15 inches. And now it's going to be the cosine of that angle, right? And then lastly, we go to the normal acceleration, and we're going to actually be able to find this value. So we can either do it up to the side or whatever, but we'll see here that's going to be positive, right? This is definitely positive, and it's going to be that AB, which was given to us as 2.95 squared, and then that length, and then don't forget to take it in the sine of 22. You could save yourself one calculator thing by like finding that out right away. 2.95, except I made 2095, 2.95. Somehow I did that. Squared times 15. So that's going to be 130.5, I think. Okay. But no, I mean, because I'm going to need to calculate that again down in the x direction. So I'm just giving you like a little bit, hey, you want to save yourself like 2 seconds worth of calculator plugging and chugging. And I'd also make a pitch that like when I see in between numbers and I see that you got the in between number wrong, I found out that it's just a math error, right? I could potentially think there was a concept error. It's tough to like identify which is which, but a math error is small. concept error a little bigger. But we get that alpha AB. We can see that we've isolated that and we can get it. And I'm not going to plug it in, but it's down here somewhere. Ooh, she gave me, and we got a negative, right? So I believe, yeah, it's a negative here, 158.72 radians per second squared. So that guess was incorrect. But you kind of could have known that, or you could have suspected it. It's not quite, with velocity analysis, you can rationalize your way out, but because of the influence of the normal acceleration, that normal acceleration could be so large as to take care of the fact that that this only has horizontal, right? So that it's not necessarily, but we could have like a suspicion, but we did get this wrong. So in the X direction, when we go to write it, as we alluded to before, I would just write this as positive, right? Just say this is, now it's no longer a hat, it's just a magnitude. And if it's negative, we know it's going to the left. If it's positive, we know it's going to the right. So I didn't even bother drawing it onto here. So this, we're going to take that positive because it's in the positive direction. But now it's going to be the cosine of 70 degrees. And now we want to, this is drawn as positive, so I'm going plus right there. Right, so this is what we referred to earlier, like if we got the wrong thing. So that plus means the diagram, but inside I'm putting the negative because I know that I got it. It's actually different from the diagram. And then 15, and then now it's going to be the sine of 22.08. And now here, this is also positive direction. So that's going to be 130.5. See, I just saved that. That's where the time got saved. And I believe it will actually be a positive value, even though that negative was in there. It did turn out to be positive. So it's a 46.87 inches per second squared. And we should probably, one thing is sort of a sticking point with me, rewrite this out. And please don't give me a negative sign and then an arrow. I prefer arrows. And I'm reminded of my father-in-law who passed away not long ago. But I would amuse him sometimes. He would talk about doing something on the microwave. He and I both do the thing where if something needs to be 1 minute, I'll hit it 111 because I save time by not having to go from 100. I didn't have to take the, and I'm saving time. He mentioned that, and I asked Bob one day, like, what are you going to do with all that time that you saved, you've accumulated over the years, all that saved time? It made Bob laugh. Making Bob laugh was a fun thing for me. Okay, so let's try this thing. We'll tackle it with vectors. All right, so I missed Bob. Vector math. Well, especially since they're not triangles, right? But I guess if you got used to it, it would be worth it. But it's just a little bit of an investment in it's just more things to have to like remember. I have to barely do the vector triangles. All right, so what we kind of need in the beginning here is almost to do, we do need the, do we? No, I don't know. We'll start out with writing down with what we know. We know that omega AB is, they say counterclockwise, so it's 2.95 K, and it was positive, right, because it was counterclockwise, radians per second. Yeah. And what else do I need to know? Well, see, let's just write down our main equation and double check where we're, because I don't have the answer of this done right here. So I have to actually think as we're writing stuff down. We're taking the acceleration of B plus alpha AB K crossed with R A with respect to B. I've seen people get this backwards, B with respect to A. Just remember, you might want to go back to the fundamental of the thing, you know, as you're saying, the acceleration of B plus the acceleration of A with respect to B, right? And the with respect to says that right there, right? That's the reference. It's with respect to that to be able to get to that. So just remember, when you're writing out the position vector, it's the same as this, right? That we're using B as the reference, so that position vector also has to be with respect to B. And then for 2 dimensions, that makes this minus, and then it's just going to be multiplied, once again, A with respect to B. So we need the radii, yes. And we also need this, right? So we're going to have to, we might want to start out, like maybe, I'm thinking as I'm, you know, like maybe if I had pre-thought of this, we also need to write out the acceleration of B is equal to the acceleration of O. I just made that into a theta accidentally. And I'll write out the entire thing, even though it's not necessary. K crossed with R, B with respect to O, minus omega, they called it O, so I'll keep that way, and then R, B with respect to O. So we were told that's 0. I mean, this is stationary, so we didn't need it. So we needed, so amongst the things we need that vector right there. So R, B with respect to O, it's going to be in the negative x direction, right? Because we're looking at B. So it's going to be a negative 6 times the cosine of 70, I, and it's going vertically up positive, so 6 times the sine of 70, J. So that's going to be a negative 2.052 I and 5.638 J. Whoops. Inches. While we're here, while we're getting the radiuses, we get RA with respect to B, right? So we're going to look down. So both of them are going to be negative, right? Because we're going to look to the left for A, and we're going to look down. So we're going to have a negative 15, but now it's going to be the cosine of 22.08 I, and then also a negative 15 sine of 22.08 J. So 22.08 cosine 15 times negative 13.9 and 22.08 sine times negative 5.639 J inches. Okay. So we start with our acceleration at B is going to be negative omega 2, which is 20, omega 0, which is 20 squared, times our negative 13.90, and minus 20 squared times our negative 5.639. You're right. It was just above it, so like, thank you so much. Yeah, sorry about that. So yeah, negative 2.052 And that's so easy to make silly mistakes like that. Is it the same value? Yeah, that makes sense. It's the same y value. Duh. Yeah. Right. Yeah. But this should not be negative. This should be a positive one. Right? This is negative, but this is positive. So we're looking up for this one. We're looking down for that one. So let's see. We had a negative, so they're going to cancel each other out. So we're going to get 400 times 2.052. Boom. So we get 820.8 I plus, that should be a negative value right there. I'll flop them there, just multiply it by 400. And we get a negative 2,255 inches per second squared. So we come back to having to do this equation right up here and start working through. We're gonna, I didn't actually need to write this right here, right? Because we already knew that we're just gonna square it anyway. Yeah, all right. And something we should also say, acceleration of A, we can write that the acceleration of A is going to be only in the I direction, right? So it doesn't have a hat, so that's just the magnitude of him, is going to be the acceleration of B, which was our 820.8 I, plus our negative 2255J, plus the acceleration of AB, and that's going to be crossed with RA with respect to B. So first, it's going to be multiplied by that negative 13.90, and then we're going to take a K and cross it with an I, to the positive J, and we're not going to have enough room on our page here, so we're going to have to go down in the virtual carriage return. So we're going to alpha AB times our negative 5.639 K crossed with J, which we know is a negative I, minus omega AB squared, which was our given to us as 2.95 squared, but we have to do it multiplied by the negative 13.90. Once again, negative 2.95 squared times our negative 5.639 J. We collect on terms. We could look through here and recognize, we have 0 here on the left. That's going to help us. We get 0, negative 2255. That's supposed to be a 5, I think, right there. This guy right here, this should be negative, right? So I'll stick him negative. I'll stick him in front for some reason. Yeah. And then for this guy, I think it's a 9. So let's see, alpha AB. I believe we'll get a negative value, maybe. We'll see. So if we take the 2255, and we'll take the 2.95 and square it and multiply it by the 5.639. Boom. But that's going to be right there, but it's not, this is not a large value right here. This is only like 49 .0. So if we wanted to find it as an in-between number, 49.07 is what that ends up equaling. But this one's negative, but he's going to come up to the other side. So we're going to have this negative 2,255 minus the 49.07, and then divided by 13.9. And I get a negative 158.7. Is that what I had before? Wee-hee, yay. Yes, that tells us that it's clockwise. So we've kind of sort of virtually guessed, right? We kind of virtually guessed at it because when we used a positive value right here, that was our essentially guessing that it was going to be. And then we do it for the I direction. It's just cleanup, right? Where we just take this and equals 820.8. And then for this one right here, we stick in that negative value, negative 158.7, but it's multiplied by this, which was negative, but you can see that we had a negative I right there, so be careful with that. We'll just stick them in there. So I definitely said I went negative, negative, so that's why that's positive. And then our last one is this guy down here, which was also, we could also say that that's a negative negative if we wanted to, so we just go plus 2.95 and 13.90. Well, that's what we squared. And I think our trust issues can be resolved that we would get the same thing. I'm pretty sure. You could try it out and see if I mess something up along the way. So there's vector math for that.
Do we have any Coriolis acceleration problems?
I don't have any historically. We've never covered it. You're the first group of people that I've ever covered it with. I might have done it last fall. I don't know. I think I did it last fall. I don't think we should. Yeah,
There's just so much room for error.
I think the only thing what I haven't done is I haven't done any multiple choice or short answer kind of things in a long time, but I don't think I would do the multiple choice. I think I would ask something so I could, so a lot of times there's only a certain amount that I wanted to get out, either that I'm looking for to try to measure. So asking you to solve an entire problem all the way through just makes it really long, when maybe I just say, find the ICR of then I could ask two problems. I could ask two ICR problems, right? Just find the ICR. Then I could trust that, if you could find the ICR, given in just a little bit more concentration, you could find what the legs of the ICR are going to be, right? And then you could. So I mean, I'm thinking out loud, but yeah. So you could identify which of these has Coriolis acceleration. Yeah, so a link needs to be rotating and changing length, and then okay. Could you do the rest of the problem if you had someone, for whatever reason, some bad person said you must do it? I don't want to trigger somebody by saying, but anyway. Say it again.
How would you know what the link was going to be like using ICR?
No, you wouldn't. No. I don't want to mix the. I was saying that there were two separate for instances. For instance, I might write a problem that was like find the ICR. And then another for instance, I might write a problem that was like identify which of these has Coriolis acceleration. Right, yeah. I was not. All right, requests. I can give you the buffet, show you what the menu items are.
There's an angular kinematics one.
Yes, true. You keep doing the pages, man.
It was a motor, a flywheel.
Oh yeah, that was my fault. I'm all about the engines, man. I love engines. I love the smell of diesel. I love the constant sound in an engine, the warmth of the engine radiating as you go and see, vibration. Beating on ships are awesome. 15-inch radius flywheel rotating freely at 1800 RPM. Why freely? Why are we saying freely? I don't know what that means. Why did you write that? I don't know. It is subjected to a variable counterclockwise torque, so it isn't freely, is it? If it's got a torque on it, which is first applied at time t equals 0. The torque produces a counterclockwise angular deceleration. Oh, I see what I meant. Okay. Alpha equals minus 4t, where t is the time in seconds during which the torque is applied. That's really convoluted. All right. The time required for the flywheel to reduce its clockwise angular speed to 900 RPM. So it started out at 1800 RPM, just spinning, and then all of a sudden a torque is applied to it, and the results are that deceleration. We're going to find the magnitude of the acceleration at point A on the flywheel when the angular speed is at the same one as part A, and the time required for the flywheel to reverse its direction of rotation. All right. And this was how many years ago? 9 years ago. That's crazy. That's crazy. It's just sitting right here in front of me. That's such a little tiny window for you guys to be looking at. To think how I want a screen that's okay. So the first thing I would do is turn this into radians per second, right? Because that's our base unit to the thing. So omega 1 was 1800. Remember that it's rev per min. So we want to multiply by 2 pi rad per rev, and then divide by 60 second per min. And we get 188.5 radians per second. That says radians per second. Same thing true for omega 2, but you could just divide it by 2, right? So we don't have to write the whole thing out. 94.25 radians per second. We're given the acceleration as a function of time. So that kind of leads us down the path of the acceleration is omega dt, right? Therefore, d omega is equal to, yes, bless you, alpha dt. So we can integrate that. D omega from omega 1 to omega 2 is going to be equal to the integral of this alpha, which is negative 4t dt, starting out from 0 to whatever time we want it to be. So we end up finding we have omega 2 minus omega 1 is equal to negative, and I skipped a step, but that's okay. I think we could do that. 2, and then we could say 2, it's just t squared. Yeah, sorry. The way I have it written there, I don't know why I wrote it that way. That's okay. So all we have to do is say t is equal to the square root of omega 2 is 94.25 minus our 188.5 6.5 divided by -2, right? And that's going to work out. So we have the time is 6.8. I only gave one 3 sig figs, but there you go, 6. So for part B, we want to find the magnitude of the acceleration at point A on the flywheel, right? Yes.
So for A, I went about using the omega t is equal to omega naught plus acceleration times t. I just plugged it in and solved for t. But that gave me a different answer. I'm wondering why that doesn't work here.
Say it again.
So we have omega in respect to t as a variable is equal to omega naught plus alpha t, and then we have omega 2, omega 2, which is 94.25. I said that equal to 188.
Okay, there's way too many numbers. I'm sorry. I'm having a hard time following.
So I did this. Okay, I plugged in.
That equation is only true for constant acceleration.
Okay.
This is not constant acceleration, it varies with time.
Right.
It's a function of time.
Okay.
So you cannot use those equations, the constant acceleration equations. The only thing that's true if something varies with time is this.
Right. Okay.
So what you've written out is that equation that you had what it is actually this equation, but integrated with that as a constant. Right, but it's not a constant, so you can't use that formula. Really important. So like for B, they want the magnitude of an acceleration right here. So you have to, the magnitude is the operative word. We know that there's going to be 2 separate accelerations. There's going to be an acceleration due to just the normal acceleration, right? So there's going to be one going inwardly, but there's also going to be a tangential one. And that tangential one, we might actually, I could have asked for the total acceleration as a vector. We could have asked for that too. So if we ask for the total acceleration at that point A, we want to make sure that we have, and in this case, it would be upwards, the tangential one would be, and it would be inward, right, for the normal. So I'm trying to think how I would write that for this. Forget about it. I'll just. I was thinking about how to write it out as vector. No, no. Anyway, we'll have an squared plus at squared. Sorry, I should have put it like that. Thank you. Yep. So the acceleration of A in the normal direction would be omega squared times the radius, which is going to be, at that time is going to be the 900 RPM. So we want to use the 94.25 squared. And the radius, they told us it was 15 inches. We'll keep it in inches. So if we do that, that's 133,200 inches per second squared. That's a big number. And then the tangential one is alpha r. Alpha, oh, we didn't get it. What we need to do, we need to get what alpha is. So n aside is, it's going to be a -4 times 6.86, which actually turns out to be 8.865. So that's actually, yeah, anyway. Comes out to -27.46 radians per second squared. So -27.46 times 15. So that should be -411.9. And, you know, this is a failing of planning out ahead to make these numbers. this thing is so large compared to that when we go to do the magnitude, it's not going to really have a whole lot of an effect. So 133,200 squared plus negative 411.9 squared, you get 133,200 because it doesn't change. It didn't change it at all. Well, it was the best of intentions. What can you say? And then it says, find the time for it to stop. All right, and then how did I do that? Let me see. So what I could go back to up here, I could go back up to there, and I could, the time to stop is going to be 0 minus, oh no, the time required for the fiber to reverse its direction of rotation. That has to, so I guess you're implying it's from the very beginning, not from that. So there's sort of like a problem with the way it was phrased, to make it very clear, from time 0, not the additional time since after the 900. I think that's, yes. So they go 188.5 minus 2 t squared, so we get the t is equal to 9.71 seconds. Yeah, no, I'm a better exam writer now, I think, than I was 9 years ago. I tried to, I hope so, learn something in the past 9 years, and just hope.
Can we do the last problem?
The last problem.
Acceleration analysis?
Is it the one that looks like that? All right. I seem to recall my having written that out in my own hand not long ago. So let me see. I prefer the way that I write it. That could be just because I'm a control freak. I don't know. Maybe. No. No. One more. One more. All right, I'm gonna give up. I'm about to give up. Yeah, I'll just go with. My good friend Sean. I miss Sean. Sean's good guy. All right, so arm AB has a constant angular velocity of 16 radians per second counterclockwise. At the instant when theta is equal to 60 degrees, determine the acceleration of collar D. So it's constant. That's good. We'll start out with this guy. And so it's acceleration. Well, actually, we need velocity. They didn't do a velocity analysis for us. So counterclockwise, going that way. So we're going to have a velocity VB going in that way. And VB is going to be equal to 16 times the length, which is 3 inches. And he said in his that he was going to give it to us, but I said I'm going for it, man. So we get 16 times 3, go 96. While we're here, we get the acceleration of B. Excuse me, 48. Sorry, I don't know what I did then. That makes a lot more sense. So this right here should be, let's see, this is omega AB. And so this is going to actually be the acceleration of B with respect to A in the normal direction. It's going to be (16 squared times 3). So 16 squared times 3 is not written down. It should be 768. Exactly, 768. His trust issues are apparent.
So it's only the normal direction because it's just rotating?
Yeah, just constant. It's the constant angular velocity part of the thing again. And then probably want to do an ICR of this. So if we did an ICR, extending the link upwards and into space, we would get right up there. And did they give us this angle? Let's see, can we figure that angle out? Yes, we can. Takes a little bit of effort to find this angle right here. It's not terrible. We just need to find this dimension right there, right? So yeah, he did it on his page right there. So we'll say that, I don't know what to call this, YB. YB is 3 times the sine of 60 2.598. So this distance right here is going to be, I'm just going to write the thing out. It's going to be 6 minus 2.598, 3.402. So you're going to be beta. Beta is going to be, that'll be rise over hypotenuse. So that's inverse sine 3.402 divided by 10. I get 19.89 degrees. Does that agree with him? Oh, he went the other direction. Did he go the other direction? He has 70.12. Yeah, okay, that sounds good. Okay, let me look right here. This is going to be also 60 degrees. Anything else I need? Oh yeah, I was doing the ICR. That's why I was doing this. I'll draw that down below. So we had, it's going to be up to there. I'll exaggerate. And so this right here, let's see, this angle right in there is going to be, that's going to be our beta. This, I could draw this larger triangle right here. This right here is going to be 30 degrees because this right here is 60 degrees, right? Because that was, this line is the one that was in line with this original piece that made that 60 degrees. So this is 30 degrees. This is 90 degrees right there. So this angle is going to end up being 180 minus 30 minus 90 plus 19.89. Did I do that right? 180, 30 minus 90 minus, and then
What is that really thinking? Is that,
where?
is it a 5?
That guy?
Yeah.
I don't remember what his name is. Yeah, I would call him Phi. Yeah. I don't know why I have like this mental block that I can't remember my Greek letters. I think I just lost my place, but I believe I get 40.11 degrees. Did he tell me that? Well, no, he didn't, but we could test it out with this right here. All right, so here you go. This is a good candidate for our law of sines. Let's see, this is our B, and this is D for whatever reason. So that's B with respect to ICR, and here's R, D with respect to ICR. This does not equal that. So this is length, this is 10 inches right there, right? So if we want to get the R, because we know the velocity, so we need the RB with respect to ICR. So that's going to be the opposite of this angle, and that's going to be sine of 90 plus my, I should be able to do that in my head. What's 90 plus 19.89? Is that 109.89? And we want to take the length of this, which is going to be 10, and divide that by the sine of 30. So RB with respect to ICR. Let's go. Actually, I didn't need that angle right there. All I needed was, is that true? Yeah, that's all I needed. Okay. So 10 divided by sine of 30, that's 200, and then multiply by 109.89 sine times, I get 18.81. So omega, oh, and this was a velocity that was coming up that way, VB. So omega BD can be VB divided by RB ICR, or 48. Can hope. What just happened? I don't know, I hit a button. All right. 48, 18.81. Please be right. Please be right. Yes, got it right. 2.552 radians per second. Stand the wrong way. Okay, so we got the velocity analysis out of the way. So we go to the acceleration analysis of this. And I'll try to. Well, if it wasn't asked for, we could do it, right? Then we would, get the RD with respect to ICR is now going to be, well, we should do this. The sine of this would be the 40.11s, and then we'd still have the 10 over sine of 30.
How do we know that we don't need the velocity? What told you that?
Well, we need the angular velocities for acceleration.
Right.
We don't need to know the actual velocity of D to be able to find it. So we could save ourselves a little tiny bit, but it doesn't hurt to find it, right? So we could find RD with respect to ICR is now going to be, 10 divided by, I know what that is, sine of 30, but I still did it. And now 40.11 sine times, so we end up with 12.89, call it, And so the velocity of D is omega BD times RD with respect to ICR, or 2.552 times 12.89. We get 32.88 inches per second, which is also, by the way, it's going to be coming that way. I'll just write that a separate piece of paper just because. Nah, I can fit it on there. I'm gonna try to make my diagrams look right. Ah. This is why I could never teach a 3-hour class, because my attention span gets like really, really bad, like right around now. Like my head gets kind of swimmy. And I'm like, focus. Okay. When I took my master's degree, every class was a 3-hour class. We met once a week for 3 hours. That is not fun. But people teach 3-hour classes. People do. All right, so this acceleration right here is downwards, right? This is the acceleration of B, and this one has to be horizontal. So we take the one that we know, and apply it to both places. Where's the angle on this? Sorry, so the angle should be like right there. That should be 60 degrees. Acceleration of B. And because we're using this, yep, that's the reference. We have this, and that. Let's not forget our angles. Our angels or angles. That right there is just the one I call beta. And this is the acceleration of D with respect to B, normal direction. I'm going to guess counterclockwise, so that's going to be my BD right there. So that means that's going to be up this way. You too have a great weekend. Acceleration of D with respect to B, tangentially. This right there is also beta. Sure. So once again, the thing that's going to probably be the best is to take it do it in the y direction, because we makes that equal to 0, right? So the main equation that we're writing out for as a vector is for D, right? We're writing out the equation for this top part. So that's going to be acceleration of B plus the acceleration of D with respect to B, tangential, acceleration of D with respect to B, normal. And in the x direction, 0 equals to negative acceleration of B. We found all the way at the top back here was 768. Oh, did I say x direction? Sorry. Because I don't know if it's going to the left or the right for 100% for sure. The gentleman who wrote out this solution that I have in front of me actually made it to the left, but he also made his guess to the right. I think it's a hazard, personally. But anyway, let's see. So right here, we made it. Fortunately, it is downwards, so it is still negative right here. So I've just written it for like right there. We have to make sure that that's going to be the sine of 60 degrees. And then here I've assumed it's going to be upwards for the tangential. So it's going to be plus, and it's going to be alpha BD times the length, which is 10 inches. Here it's going to be the cosine of the 19.89. And then it's going to be minus the omega BD squared. And omega BD was 2.552 squared times 10, but times the sine of 19.89. And that should get me the alpha BD. So he has it written down differently, and he guessed clockwise, and he got a negative value. So I should get a positive value. I guessed positive. I should get a positive value. I've thought about like rewriting all of these out in to my preferences, but like so our 768 and 60 sine times, okay. And this is also negative, so we're going to add those two together, and it can flop over to this side. Yeah, it's going to be a positive value. Yeah, it's going to be a positive value. So I guessed right. I should give Sean a call. Pick on him. No, that's not true. Laura used to say that he was my man crush. We got along really well. He's a good guy. I get a 73.09. And it's positive. And that's the same thing my good man Sean Winnis got.
I have a question. So the third diagram for the rotation.
Yep.
So when we're drawing that, do we pretend that like D isn't constrained? Like is that like
Yes.
okay.
Yep. We're just pretending like it's pure rotation because we used
B is like the reference thing. So so we go in the X direction. And now I'm going to leave AD as I'll just leave it as positive, even though I didn't draw it on here as positive, but I don't necessarily know. Okay, so right here, this is a portion of AB is negative. So 768, and now it's going to be the cosine of 60. There. And we got this right, so but he's also negative as drawn, and so it's going to be that's the alpha. I'm going to have to squish stuff in here, unfortunately. 73.09 and 10. But now it's going to be the sine of beta. And this is also negative, so I think everything's negative. 2.552 squared, 10, and now, but it's going to be the cosine of that angle. And AD is equal to, so let's see, 10 times that, 19.89 sine times that, okay. So that portion, and then go 768 times 60 cosine. I'm going to add them together because I'm using positive stuff right here. And then the last one is 2.552 squared times 10 times 19.89 cosine times, and add them up. And I get negative 693.9 inches per second squared. So yay, we got the right answer.
So in what situations do we just not label, like, when do we not guess the direction? Like here, you just guess which direction the heat's gonna go.
I mean, it doesn't hurt to draw it on there and to draw it positive if you were going to guess, but
So it doesn't have to correspond with the diagram on the right, like it does for the velocity diagrams. It can go in a different direction.
it's all because the influence of this normal direction really kind of like messes it up to try to use intuition sometimes to guess, right? Because this can be a pretty big valley, right? Especially since it gets, whatever the angular velocity was, it's squared, right? So this could have a big effect on what the results are.
So even though it shows the accelerator, like the acceleration is going this way to the left,
Yeah,
it
I
can
mean,
go to the right.
honestly, the truth is, once we found what that was, and we saw that we got it correct, everything went to the left, so it's kind of obvious.
Okay.
So after the fact, I personally probably would have drawn it onto here. So me as an instructor, when I see your diagram, I don't know what order in which you did with that.
Right.
You're welcome. Have a great weekend. I think you could call it a matter of personal choice, but you only risk sometimes making a guess. I think the biggest risk is to make a negative guess. Sometimes to make two or make contradictory guesses, and I think that could have a problem here. If I made a guess on my diagram and I made this negative, and then I found out like, I got I might think I get a negative answer. I'm like, well then I must be wrong. You can double negative yourself, right? And yeah, I get the wrong direction. So it's almost better for me sometimes to just draw it on, to not even draw it on there, just to assume that it's just going to fall out to be whatever it is on the diagram.
That's 60 degrees for the middle on the top part.
That part?
Yeah.
Yes. It just didn't fit in there very well. Because I was measuring it with respect to horizontal. I got some good stuff in here. Got another request.
Can we do the rigid body motion velocity analysis?
Okay. Is that a particular one?
It says problem 15.7.
Okay. Flip. This guy?
Yeah.
He's a roller. All right, so solve either by vector triangles, vector components, or ICR. So we could solve this in any of those ways. We'll see that this thing is 6 inches. That's 14 inches. That looks like it's also 6 inches. Knowing that the distance AB is 5 inches. Okay, no, AD. So you too. And the distance BE is 4 inches right there. Okay, so that's 4 inches. from there to there, and this is 5 inches. Could make you think that it's 6 inches, but of course it's inside the rim. Determine the velocity of point E, right?
Have a good one.
You too. Oh, there he goes. He says, so D is moving to the right at 6 inches per second. All right. So right here, we'll say that we know that this right here is going 6 inches per second. It's moving without slipping, so that's something that tells us that this is the ICR for this wheel right here. And this is 6 inches right to there. So omega, let's call it AD. It's going to be VD over, call it the radius RD. I don't know. So 6 divided by 6, we'll get, this is 1 radian per second. And then we look up to here, this is point A right there. We could see this is going to be the VA, is going to be the omega AD. It's going to be 5 plus 6, right? So that's 6, but here is 5 up to there. So I don't know what to call that. Call it RD plus RA, whatever. 1, and this is going to be 11. So 11 inches per second is the speed of A. We could also take a look at B right here. So we isolate B. It too is moving without slipping. So there's a little bit of a trick right there that we recognize that its ICR must be like this right here. Right? So its velocity has to be in that direction. And we have to play around a little bit with our distances. So this distance is 4 inches. And this distance is 6 inches. Is that true? Let me see. No, wait. Yep, it has to be, right? This thing is a radius is 6 inches, so this must be, that's in line with this. That's 6 inches, yep, 6 inches. And I drew this velocity in that direction right there. Honestly, it might not be in that direction. And you could picture this thing as it's rolling. This thing could be rolling backwards towards it, right?
Yeah.
So let's think about that for a second. I'm almost tempted to draw the big ICR of this. Of course, this is going to be a really big triangle, but it's going to go through this right here and straight up. So because this velocity we've established is that direction, so yes, okay. So we confirmed by going ICR that yes, that is the direction of VB. All right, so, well, first off, we want to establish this ICR. You're okay with that ICR?
Yeah.
Okay, so that's going to be the omega AB, because here's a velocity of A right here. And that velocity of A establishes that this thing must be rotating about the ICR in a counterclockwise direction. And then we can also take it and look, and we could see from that, yeah, I agree. Velocity of B has to be also going, with respect to this right here. So we also can tell from this that omega BE was traveling clockwise from this. So some of the angles or some of the length, I don't have a really good place to put it in here. Let me see. I want to put it right here, and I want to, maybe I'll erase a little bit of that tail of that arrow, and I'll call this beta. It's going to be my angle of beta, where beta is going to be the inverse tan of 6/4. Or 56.31 degrees. And now maybe I want to go with my ICR. Maybe I'll go with my ICR. I'm going to redraw it up here so I get a little bit better, get more room for my, oops. Yeah, I guess it's fine. Yeah. I didn't really make a great job of this, but it's okay. I'm going to come up to that and do that. So I also need to find some geometry of this angle right here. And so that, it looks to me like is just, we would find, I'm going to call this one not beta, because I already used beta. I'll go phi. Right, and so phi is, I have the opposite from it, which is 5 inches, and I have the hypotenuse, so I'll take the inverse sine of 5/14. We get 20.92. And that's going to be this angle right there. It's also going to be that angle right here. And remember that this angle, that big angle right there, was 56.31. So this interior angle right here is going to be beta minus phi, or my 56 minus the 20.92, or 35.39. So lastly, I'm like out of like my favorite Greek letters. Oh, gamma would have been good. I went with pitchfork, which is psi, right? PSI, psi. Pitchfork. Actually, this other one looks a lot like pitchfork. I think the other one actually might be pitchfork. I don't know. That's going to be 180 minus 35.39 minus 90 plus 20.92. So what the hell is that? 90, 20.92 plus 180 minus. So he becomes 33.69. There's a whole tons of opportunities here for me to screw something up. So here's going to be my RA with respect to ICR, and then here is my RB with respect to ICR. So I need law of sines in this monkey. And was that? Yeah. What's up with that? The first thing I want to get is the RA with respect to ICR. And he's going to be opposite from the sine of 35.39. And the known length is the 14 inches. And I'm really suspicious of this 33.69, to tell you the truth. But we'll take it on faith and maybe diagnose it later if we mess the thing up. So I have sine of that, and 14, and divide by, take the inverse of it, and I'm going to flop them out, and I'm going to take the sine of that and multiply it. And I'm saying that I get 14.61 inches, so not too much different. Definitely not drawn to scale. But let's see if my omega works out here. Okay, so I can, I might want to go and find the other one, but I'm really suspicious of my angles. So my omega AB should be equal to my velocity of A divided by RA with respect to ICR. And velocity of A was 11, 14.61. I got points. Ooh, that's bad. Yeah. It is not looking good for the home team here. He says omega. Oh, no? So he jumps around here. His solution is a little confusing. I'm looking for omega AB. And I don't think he writes it out. I think omega AB should be 0.7527 radians per second. But he's got a weird thing where he never actually finds it. It doesn't look like that to me, at least. He has a relationship. He finds a relationship between them. That's a weird way to approach this thing. Let me see if I get the right answer if I keep going with this. We need the RB with respect to ICR. RB with respect to ICR. Then take the sine of, We have add 90 and 20.92. I don't trust myself to do that, so I'm gonna. It's 110.9, and we'll say that's going to be 14 and divide by the sine of 33.69. So 14 and 33.69, 33.69 sine divide, okay? And we'll take the sine of that and multiply, and I get that this is 23.58 inches. So we're saying that the velocity of B is equal to omega AB times RB with respect to ICR, or 0.7527 times 23.58. Boom. I'm getting it 17.75 inches per second. And I think I saw him, wait, no. Yes, that agrees with him. Okay, good. Okay. He just never found the in-between thing, which I think is kind of messed up, but that's all right.
Where did you get the sine 110.9?
I added that 20.92 with the 90.
Oh.
I should have written it out somewhere, but I ran out of letters. Yeah. I'm trying to think of a better way to organize this to present it, but I don't know. Continuing, so the thing we were looking to find is the velocity of E. So we have like a couple more steps to go. Now that we have the velocity of B, we can find what omega BE is going to be, right? What we need is this length right here. So that length, we could say that that's going to be, okay, so this is another ICR. It'd be nice to have to give this guy a name right here so I could give you what that length is. Yeah, no, yes, yeah. We just go, but I'm looking to try to label it correctly. Like, let's call that F. So we go R, B with respect to F is, as you say, the square root of 4 squared plus 6 squared. So 4 squared and 6 squared, which you should probably do in your head, right? Ends up being 7.211 inches. So if we want to get omega BE, it's going to be the velocity of B divided by the RB with respect to F, or 17.75 divided by 7.211. I actually have that in my calculator still. So we get that it's 2.460 radians per second. And now we can come back up. I could even just do it on top of this diagram right here, right? It's going to be that, VE. So that just means it's going to be 6 inches times that omega BE. Or the velocity of E is going to be equal to omega, did I call it DE or BE? It should be BE. I think it's BE. Yeah, it should be BE. Times, said our radius of E. 2.460 and 6. You better be equal to 14.77. Which is the answer.
says RE, right?
Was that?
That's RE, Omega B times RE.
Yeah, it's supposed to be an R, yeah. The ugly R. I was just trying to think of the name to call the radius of this. Yeah. We could also call that RE with respect to F. We invented that F as being the ICR of that root. Me too. I'm tired.
Can I just see what you wrote down for S13 angular RPM angular kinematics? I think it's a finish right now.
Which one?
It was the one about the motor.
Oh.
I'm gonna shut it down.
Is tired. Did we keep everybody engaged here? Did we get, no, not, Jacob left at some point here, so let's stop recording here and go stop recording.